The last case that we need to consider for the problem of solving Ax equals b is when the matrix A has a full row rank. What that means is that every row of A has a pivot. So you see, when you carry out elimination, you will never get a row of zeros. In that case, what you get is that Ax equals b always has a solution. So in this case, Ax equals b always has a solution. And the uniqueness of the solution will again depend on whether or not A has a null space. So if the null space of A is not 0, so if it's more than 0, then Ax equals b has infinitely many solutions. Now, when would you have a unique solution in this case? Only when the matrix is square. If the matrix is not square, then you will have infinitely many solutions. The strategy of approaching this problem is again the same. We start with writing the augmented matrix AB. So we have 1, 1, 1, 2, 1, negative 1. And then we have the vector b. We carry out elimination in the usual way. So we get R2 minus R1 into R2. We get 1, 1, 1, 3, and then 0, 1, negative 2, 1. And because we don't want to just stop at u, but we want the reduced row echelon form, we also have to eliminate above the pivots. The operation is R1 minus R2 into R1. And we get 1, 0. Then 1 minus negative 2 is 1 plus 2, so you get a 3 here. Then 3 minus 1 is 2. And we have 0, 1, negative 2, 1. And we have reached, so we have started with the system AB here. And we have reached the system RD here. The intermediate system in this case was UC. It's not important that I stated, but just for completeness of our understanding. And we get through these systems via elimination. Now, because we have, so where are our pivots? Let's focus now on R. We have 2 pivots. Those are our pivot columns, and so we have a free column. A free column means that the null space of A is not 0. There is something in the null space of A, and it is actually very easy to see how to get a 0 by combining these 3 vectors or the 3 columns. Our strategy, so again, we find a special solution to Rx equals 0. So the first step is to solve Rx equals 0, which also solves simultaneously Ax equals 0. Then how do we do that? By looking for special solutions. We only have one free variable that corresponds to x3. We set that variable to 1. And then using that variable, we find x1 and x2. We start from the second row, so we focus our attention right here. Remember, we don't worry about the values in D because we're solving the system Rx equals 0. So we have x2 minus 2x3, so x3 being 1, this really means x2 minus 2 must be 0. Well, that means that x2 must be 2. 2 minus 2 gives us 0. And then we do the same thing in the first row. You see now that the second pivot variable doesn't show up in the first equation because we carried out that elimination upwards as well. So if we were to use u, we would have to replace whatever we have for x2 in that equation. Whereas here, we only the free columns affect that one pivot. So we have x1 plus 3 must be 0. That means x1 must be negative 3. And the solution, the special solution, I guess I should say the special solution here, S, there is only one, is negative 3, 2, 1, whereas the null space solution from here would just be any constant times negative 3, 2, 1. So this is the general form of the null space solution. So this is general form because C could be anything. That is up to us to choose. Then once we have solved Rx equals 0, our second step is to find one particular solution to, so find XP that solves Rxp equals D. This is equivalent to AXP equals B. So how do you do that? Well, again, you want to find just one, and a special particular solution will only involve the pivot columns. That means that x3 is going to be 0 because I just don't want to consider the free column. And how I can express 2, 1 is a combination of the first two columns. Well, it's just 2 times the first column plus 1 times the second column. So because we have 2 times 1, 0 plus 1 times 0, 1 plus 0 times 3, negative 2 equals 2, 1. Again, this is not unique. There are many particular solutions. This is just one of them, and it's the easiest one because you work with columns of the identity when you put 0 for the free column. And this gives you the particular solution equal to 2, 1, 0. So these coefficients are the 2 from here, the 1 from here, and the 0 from there. So we have the null space solution, we have the particular solution. Putting those together give us the general solution x, which is C times negative 3, 2, 1, plus the particular solution 2, 1, 0. So now any solution to the system AX equals B must be in this form. Depending on your choice of particular solution, that C might change. But again, if we're using the matrix R and the vector D, then finding that solution is very easy, as is finding the solutions to the null space problem. And we have now covered with this example the 3 possible cases that we could get in solving AX equals B. When A has full column rank, you don't always have a solution, so it could be that you don't have a solution there. When you do have a solution, that solution is unique because there is no null space. Whereas if you have full row rank, your matrix, if your matrix is not square and therefore not invertible, it will have a non-trivial null space, which gives us infinitely many solutions.